Alrighty, it's basically 6:05, so we're gonna get started. This is the IEEE tutoring 1202 final exam review. Sorry, did somebody move that? So I am in CE EE 1202. I'm just gonna let y'all know. I'm using the notes and PowerPoints from our head tutor, Jason Newman. Unfortunately, he fell ill and he had to make up a lot of work, so I'm in his stead. I can promise you, I do know what I'm talking about for the most part, so just have some faith in me, I guess. And then all credits for example problems and informational slides do go to Jason Newman and Diana Kogan, our professor. With that being said, let's just get started here. So the overview of what we're going to do today, we're just going to go over some overall concepts, maybe some practice problems if y'all are into that, and then any tricks or tips to solve and remember stuff. Any specific problems, concepts that have popped up on previous exams will be included as well. And then so from my understanding, it's not going to be all over the first part. It's mostly going to be over the last section. So microcontrollers, analog to digital conversion, communications, stuff like that. So we're going to kind of blitz through the earlier stuff, if that's all right with y'all. What are we thinking? Okay, I'm getting nuts. Let's get started. So KVL, KCL, and Ohm's law. Also, you may not want to write it down because there's a lot of stuff. There's like 50 slides. Just sit back and relax. I guess if y'all don't remember that, in any closed loop network, so specifically in a network, not a node, the sum of the voltages is equal to 0, which means I'm not going to write it out, but yeah. And then KCL, the algebraic sum of all the currents entering and exiting a node is going to be equal to 0. And then Ohm's law, V is equal to IR. Pretty simple stuff. Practice problems. You guys want me to go over any like loop problems or anything like that? Too easy? Okay. Okay.
Yeah, easy stuff.
So equivalent resistance and voltage division, collapsing resistor networks. So what's the difference between parallel and series, guys?
Series they share current, parallel they share voltage.
Fantastic. Okay, and then how would you collapse them into equivalent resistance?
You use the equivalent resistance. For series, it's just a sum of the resistors.
Sum of the resistance.
And parallel is the inverse of sum of the inverse resistance.
Sounds good. And then voltage division. So it's just going to be the voltage over resistor. And if it is a capacitor and inductor, you're going to use impedance, right? And those are the equations. Simple enough. Practice problems, we thinking of those, or we're going to move on to the harder stuff. Okay. Capacitors and inductors. So what are capacitors at DC?
Short circuit. Open circuits.
Open circuits, we agree? Okay. How would you collapse a resistor network in parallel and series?
They work backward from resistors. So if they're in series, you got the inverse of the sum of the inverse. If they're in parallel, you just add.
Yeah, so when you're in parallel, you add them, and then when you're in series, you add the sum of the inverse of the resistances, or capacitance, sorry. And then what are inductors at DC?
It's wired.
Yeah, so yeah, they're going to be a short circuit. So for those who couldn't hear me, capacitors are going to be open at DC, and inductors will be shorts. And then collapsing inductor networks, what would those be? In parallel and series. Yeah, so they will be the same as resistors. So in series, you add them up. In parallel, you will add the inverses. Okay, sinusoids and impedance. I'm going to have to exit out of this for this. So this is Jason Newman's notes. Sinusoids, we kind of all know how those work. We got all the definitions here. We've had 2 exams over this. Y'all are fine. Adding 2 sinusoids. You want to switch these over to cosine if one of these is a sine function, right? Here are the graphs for it and the phase shifts. And converting from polar to rectangular. We all got that down pretty good, I think. Phasors, pretty easy. Just a complex number. It represents the amplitude and phase of a sinusoid. You can think of it as a vector equation. So just the amplitude and the direction. Except instead of a y-axis, we have an imaginary axis. Oh, down here, actually. Yeah, so we have the real, we have the imaginary. The properties here, you can just treat it as complex numbers. Let's see. So these are all the conversions. I'm sure you guys already know this. Okay, operations on complex numbers. I think we all know, right? Okay, I'm getting nods. And we shouldn't need to know reciprocal or square root, but I do think conjugate has popped up on homework problems. Conjugate is just, you make the phase angle 0. That's it. Or not 0, sorry, you make it negative. That's it. And then these are some problems. I mean, I think you guys are fine with this, right? Okay, moving on. Next up, we got complex impedance. Let's see what we got here. Okay, so do you want to run through a complex impedance problem, or would you rather move on to the vocab? What are we thinking? You want to do like one?
We do one.
Sure, that's fine. Let me, there should be some room down here. Oh, those are buddy plots. Okay. Let me open up. Okay, I'll do it up here. And I got to draw. Okay, so. Okay, so we're gonna do one problem here. Can I draw? That's fun. No, I can't. Okay, so I'm just gonna draw in here. So I guess let's just do. I'll just make up numbers. We got this guy, right? He will not agree with me. Okay, so let's just say we got a resistor here, a capacitor here. I'm sorry, my drawing is horrible. And then an inductor right here. Okay, so I won't include any numbers just for the sake of time because we got a lot of material to run through, like 50-some slides. Okay, so how would we add these up? How would we go about finding the equivalent resistance?
In parallel, so it can be 1 over R plus 1 over C plus 1 over L.
Okay,
Wait,
so yeah, that's not entirely correct because capacitors don't add like that in parallel. So can somebody else give me an answer?
Like 1 over R plus like the. I mean, it's basically just the inverse of all of them.
Yeah, so it would be 1 over R plus C, right? Plus 1 over L. Sounds good? Okay. Yeah, but, or sorry, it'd be, yeah, R and then there'd be L. Yeah, it'd be JWC and JWL. And then, I can't find the eraser. Oh my God. How do I erase this? Okay, I'm just gonna undo all this. And then if we're gonna be adding these up in series. I got it. Okay. There we go. Okay, I figured it out. So if we're gonna be adding these up in series then, so we just got this guy, got a resistor, capacitor, and inductor. How do we go about adding these?
1 over the same way that we do it without the inverse.
Okay, so you're saying the same way but without the inverse. Can you elaborate?
That's like 1 by R plus JWC plus 1 over.
Okay, so you're saying that ZEQ is equal to what? 1 over, okay,
So
so
it'll just be R.
R plus,
No, there's
no one?
Just R plus JWC plus JW.
It'll be R plus 1 over JWC because that's it.
Yeah, oh, my bad. So it's R plus 1 over, yeah, J omega C plus J omega L, right?
Yeah.
This is a C. That won't matter. Okay, and then I guess it's easy enough. So then, okay, so we all good here then? Just whenever some of this quickly. If I put in numbers, we're gonna take like half an hour longer because it's gonna be a hassle. Okay, next slides. Let's see. So it's complex impedance, op amps. So can you guys give me the equation for the op amp? So let's start with a what's it? An inverting amp. So what's the equation for the gain equation for the inverting amp? No.
It'll just be RM.
Negative RF over RI. Yeah. So the inverting is going to be negative RF over RI. That's an F. Okay, so what about non-inverting?
1 plus R.
Okay, 1 plus RF over RI. Okay, easy enough. You guys know this stuff. Okay, then let's do difference amplifier.
It's going to be assuming that those two pairs are the same. It's RF over RI times V1,
V2 minus V1.
the one that's going into the inverting input plus the one going into the non-inverting input.
I believe it's V2 minus V1.
Sure, if you want, yeah, depending on how you label it.
Yeah, that's true.
V2, whichever one is going into the non-inverting one.
Assuming that,
V2 is going
assuming that
first.
V1 is going into the inverting.
Yes.
Okay, yeah. The large amount of answers is telling me y'all know what you're doing. Okay, and then lastly, the fun guy. What's the output voltage of the summing amplifier?
Negative with
Negative
negative RF times the sum of the currents.
Fantastic. And that's just Vn plus R of n, ... Okay, looks like you guys got this down. And we can review this slide. Oh, it's not letting me do it. We can review the slide very quickly in case y'all want to go over this. You guys want me to share the slide set?
Yeah.
Okay. So I'll share the slide set. I don't know how I'm going to do that. I'll probably put it in the Discord or something. Yeah, I'll put it in the Discord. Or we could link it in the bottom of the video. Okay, so we won't need to know the pinout, hopefully. Rails here, equivalent circuit model. The ideal op amp, that's something important we need to know. So it's an amplifier with infinite open loop gain, infinite input resistance, and 0 output resistance. That's something to remember. The properties here, it'd be finding the current, so you know those current analysis equations for op amps. I hated those. Okay, all the equations, I got that down. And alrighty, so this is where he'll be doing problems, but I'm not going to do that. Okay, gain, decibels, and conversions. So fun stuff. How would you convert summing from gain to decibels? So volts per volts to decibels. 20 log gain, right?
Yeah.
Okay.
Yeah.
So, I'm sorry?
I was just answering.
I can't. I'm sorry, I can't hear. I need to turn y'all's volume up. Okay, can you say that now?
Someone already answered.
Oh, okay, sweet, awesome, thank you. Okay, so gain decibels conversion. So volts to volt to decibels is 20 log base 10, but that's implied when you say log, and then your gain, right? Okay, easy enough. So what then are we going to do to convert back to gain from our decibel point? So you can do a lot of other fun stuff that I'm sure Professor Kogan has told us to do, but what's a very simple method that we learned in calculus? Very simple method. Converting
10 to the power of the answer divided by 20.
Right, so we just use logarithm properties. So we get gain is equal to 10 to the power of whatever we happen to get. Yeah, so that'd just be our x divided by 20, right? All to the same power. And yes, this can be negative and very small sometimes. I'm sure you guys already know that though. Okay, so half power point. How would we find the half power point of, okay, let's do it both ways actually. The half power point in gain and the half power point in decibels. So that means at the cutoff frequency.
That minus 3.
Yeah, so in decibels. So to find the half power point, that would be decibels, oops, minus 3. Okay.
Decibel at the high pass or the low pass.
Yeah, it won't matter. This is just high, sorry, not high pass. This is a half power point. Okay, and then how would we do this in volts per volt? Sorry?
It's the output voltage.
Yes, that is gain over root 2. And if you just forget on the exam, you can always just convert and then do the specific formula. Let's see what else. So I guess this one has Baud plots on it. When you're out on a Baud plot, for each decade, how much would you subtract by when you're outside of the cutoff frequency? So outside of the passband specifically, how much would you subtract by? 20 decibels? And you're going to take up all the answers. So when for each decade, so I guess I'll just do each decade is going to be our decibel value minus 20. Okay. Easy enough. Is there anything else we need to go over? I think we had an exam over this, so it's pretty fresh in our minds, but I can still go over the slide set. Like a decade? Okay, that's fine. Yeah, it's the x value to the power 10, or I can't really show you without getting up here. So it's all this. You can do negative 3.01, but McGraw-Hill will only take -3, so I just recommend doing that. And let's see, the Baud plots are not on here. The Baud plots are here, right? No, they're down here. Yeah, they're down here. They're down here. Okay. So you guys don't have any problem with the filter problems, right? I hope not. I had an exam over it. Pretty simple stuff. A lot of it, you can just use the equations here that you derived in class, like high pass, low pass filter cutoff frequencies. We know those. 1/2 pi CF, not CF, sorry, CR. Okay, so a decade is 10 to the power of. So this is 1 decade, 2 decade, 3 decade, etc. But on the exam, they will just give you the value out. Okay, yeah, so like 700,000 rounds per second. And don't forget, it will catch you up on the exam. There is a difference between rads per second and hertz. In fact, I will write this. So,
Quick question.
Sure.
Are decades counted from the cutoff frequency or from just the passband frequency?
No. So decades are going to be cut off from the passband because you just can't do that. I mean, it'll be from the cutoff frequency. No.
So from the passband.
From the passband, yes, sorry. That was a bit meandering. Okay, so what's the difference between hertz and rads per second, right? Like they'll give you omega is equal to 2000. Yeah. Rad per second. Oh my God, that is awful handwriting. Okay, 2000 rads per second, right? So how would you convert to hertz? Right. So you would divide this by 2 pi. Okay, and then obviously converting back to rads per second from any hertz value is multiplied by 2 pi. Fantastic. Okay, filters and filter examples. Do we need to go over these? We had an exam on this. Active filters use op amps, right? Golden rule of op amps. I of positive is equal to I of negative, which is equal to 0, and B of positive is equal to B of negative when negative feedback is present. Active filter circuits. These are all the equations. Again, I will post this later. And these are some problems, but you can just do those in the homework. Okay, Baud plots, we just went over those. Okay, here comes the fun stuff, and I can put the pencil down. Go back. Okay. So here is what the majority of our exam is going to be over, more than likely. That one all the way to the start. Okay. So embedded systems. They're programmable computers placed inside a device to provide added functionality, right? So we're thinking of, little microcontroller brains. They're not intended to be general purpose computers, right? And most computing systems outside of, heavy computing are going to be embedded systems. So these are things you are going to have to memorize, unfortunately. So the structure and characteristics of embedded systems, they are specialized, which means they only have one function. They usually perform their function within specified time periods. They're more than often lightweight and low volume because they need to be small, right? They're power efficient and they're inexpensive. So there are lots of them. Well, not right now, there's a shortage, but you know what I mean. 4 general embedded system needs: communication and networking. You got chips in your phones that do stuff like that. Switching and information transmission. Telephone systems and internet, kind of obvious. Signal processing, that's fun. Computation involving large data sets, like the Baud plots, that is signal processing. Radar, sonar, and video compression. Yeah, you know that already. Control systems, so it's got feedback control, flight control, and vehicle engine. So feedback control systems is a little gauge goes up and tells you, oh, there's something wrong on the airplane, right? General computing, video games, Apple Watches, wearable computers, stuff like that. I would recommend memorizing this. Microprocessors versus microcontrollers. Can anybody tell me a real life example between the two, if you can remember?
Microcontrollers, so I mean,
Yeah, you let him go.
Microcontroller, I'm sorry, microprocessor would be like a computer CPU.
Yeah,
and
CPU.
Microcontroller these best example I can think of responding equipment. Just modern.
Okay. Yeah, this guy knows his stuff. So a microprocessor is an external circuit for memory and I/O. It must be connected to the chip. So it's stuff like a CPU, a GPU, things like that. And it's mainly used for heavy duty systems. And a microcontroller, the memory and I/O functions are embedded onto the chip. That's why whenever you look in Arduino, you see all these little small boxes. That's what that is. And then they're used in function-specific devices like washing machines or calculators. So advantages and disadvantages to microcontrollers are in the description from earlier. They are more compact, and they can be programmed to perform very specific tasks, and they're cheap, but they're not customizable. Unlike your PC, you can't just rip out the GPU and put in a new one. So upgrades aren't really possible. High complexity of the chip design can lead to defects, so I mean, that's kind of self-explanatory, and they can't be used for multitasking. So the Arduino, Raspberry Pi, and Launchpad. This was on the study guide for one of her slide sets, which means this is going to be more than likely on the exam. Just take note of these. I'm sure you all know what an Arduino is by now. I would hope so. My lab partner didn't show up to lab, so I don't know if he knows what that is. We got open source hardware and IDE. Most commonly used microcontroller for simple processors, right? Projects. Sorry. We got the Raspberry Pi. More commonly used in compact computer systems for simple projects, much like an Arduino. It has its own officially supported OS, Raspbian. I don't know how to say that. Raspbian. And then the TI Launchpad that UTD used to use, actually, until we moved over to Arduinos. Okay. Oh, and actually, one other thing. It can have memory and peripherals that can be used with it. So Arduinos can't use mouse and keyboard, but TI Launchpads, I believe, can, if I'm not wrong. Okay, so this was also on one of her study guides. Baud rate, UART, 32-bit ARM Cortex M4. That last one's a mouthful. You can just call it the ARM. So UART communication, we did it in, I think, Lab 9, right? So it's just universal asynchronous receiver-transmitter. It's just asynchronous communication, which means it doesn't require a clock. That's what the baud rate's for, or baud rate, however you want to say it. The baud rate is just the number of symbols / modulations sent per second. In fact, we're going to go over that later with the signal processing stuff. So for two devices to communicate via UART, they must have the same baud rate, which is, again, what we did in the lab. And then the ARM Cortex M4, it's a widely used microcontroller brain, quote unquote. So it's a chipset that they use. You know, if you guys have ever looked into your little CPUs from like those Ryzen CPUs, a lot of modern technology uses ARM. It's just an architecture that was invented, I believe, by British people. Analog to digital conversion. There are 3 steps. Well, first of all, so I'm getting ahead of myself. It converts a continuous analog signal input, so like light, it'll be variable, and it puts it to discrete digital numbers, so zeros and ones, right? There are 3 steps in the conversion. The sampler, so the analog input will go in here. I would use the visualizers, but I don't know if McGraw will get mad if I did that. So we have the analog input for the sampler, the quantizer, and the encoder. So the digital output goes there. So can anybody other than Sebastian tell me what each of these do? If you remember. It's okay if you don't remember because those are on the slides next. Go for it.
Well, like over the course of time, a sampler, like I like a certain clock speed or like a sample rate. The sampler will take like snapshots of what the voltage is at that time.
So you're saying, I like what you said there, but simplify it for me. What axis is it turning into discrete values?
Axis.
What axis? What time? What axis is time normally?
So it's not like in the
Yeah, the x-axis, right? The quantizer, what axis does that turn into discrete values? If you guys don't remember, it's where we take the middle value and we do the step sizes and all that. You guys remember that? Yeah, so the sampler takes the x-axis and makes it into discrete values, and the quantizer takes the y-axis and turns those into discrete values. And then the encoder, y'all are in digital systems, I think, so you know what an encoder does. And the digital output will go there. Okay, so sampling, like we just said, it takes analog x values, turns them into discrete x values. Again, this is very important. So yeah, it depends on the clock frequency. Increasing sampling rate increases conversion accuracy because you have more little time plots to use. And then there's a possibility of aliasing. And again, shown along the x-axis. That's very important. If anything, if you get stuck on your exam and you don't know what to do, and you're given a little analog graph, just start with the x-axis and plot those discrete points. And then we must sample this at more than twice the highest frequency. That's a Nyquist frequency to prevent aliasing, right? There's a Nyquist frequency. I think you guys even did this in class for review. I was not there. The highest frequency times 2, very, very simple. And we do want to sample at slightly more than twice the highest frequency. Does anybody know why?
Have some separation.
I don't think so, no.
Isn't it because of like, there's a frequency like at Nyquist frequency that
Yeah.
it will just be a straight line instead of like an actual like sine wave?
So the reason we have to sample at slightly more than the Nyquist frequency is because it would just be kind of a flat line. Yeah, I'm not in the telecommunications class, so I don't know exactly what that is. Examples, I mean, what do you want me to do? Like, put 3 values and then ask you which one's a Nyquist frequency?
Sure.
Okay, let's do it then. Okay. Okay, sure. No, twice the highest frequency. The Nyquist frequency, yeah, the Nyquist frequency is twice the highest frequency, and you want to sample at a little more than that. And we're actually doing a problem right now about it. Tell me the Nyquist frequency of this guy. 8,000, right? That's because these values don't matter. This is the only one that matters. That's 8,000. Okay. Then tell me what would be an acceptable Nyquist? What would be an acceptable frequency to sample this at? Yeah, 80. Well, that's not 10%. That's 80, but yeah. So this would be an acceptable one. So it's about 10% up. Okay. Simple enough, right?
Isn't that 1% up?
Is that one? Oh, that's my bad, guys. That's my bad. Okay, yeah, that'd be plus 10%. So you guys said 8,800?
Yeah.
Oopsies. Okay. Fun stuff. Next slide. There we go. Okay. So quantization, discrete Y values. This is very important. Everything on this slide is very important. An 8-bit ADC will use 8 bits to sample each signal. So we say it has a resolution of 8 bits, right? So the Y value will tell you the resolution. Sorry, not the Y value. The Y axis will tell you the resolution, correct? That is something to remember. Again, if you blank, just think Y axis resolution. It uses 2 to the 8 or 256 different values to represent the samples collected. So again, resolution is a number of bits and values is 2 to the nth. So that's going to be 2 to the 8th. And then, as another example, 12-bit ADC has a resolution of 12 bits and can represent 2 to the 12th or 4,096 discrete values. So how would we increase the resolution? All right, we increase the number of bits used to quantize the signal. And then, yeah, okay. And then we're just going to do simplest way to quantize a signal is to choose the digital amplitude closest to the original analog value. And the number of different levels, as I just said, is n is equal to 2 to the nth. Okay, 2 equations at the bottom. Highly recommend you try to at least remember these. I did actually struggle with this a little bit on the homework because she didn't give us the bottom equation. So the quantization and step size is quite easy. You're just doing a, I don't know, like a subgraph almost. Just the maximum minus the minimum divided by, it's like an average actually, just divided by the number of levels. The quantization error, you're just going to multiply those levels by 2. I don't know why. That's what Google told me, and I got the question right. So just remember these equations, please. Okay, evaluating the converter. So error depends on the resolution, the little delta earlier, not the ADC. And the more levels we have, the more bits, it's not supposed to be necessary, we need to represent those levels, but the smaller our error is. And the more bits we use, the higher the resolution gets, but it also becomes more expensive, which is something I guess you got to worry about in the future. SQ&R. Ooh. The equation's right there. It's a quality of an ADC. So it's just a signal to quantization noise. It's just like almost like an error equation. So B is the number of bits used to quantize the signal. Do we need to do a problem for this? Yeah? Okay, so Dan is saying yes. It's okay, I don't blame you. Okay, awesome. Okay, so you know what? Let's go big or go home. Let's start with, yeah, this seems good enough. Okay, I'm not gonna draw out a whole graph, right? Don't have to. Do you guys want me to just draw out a whole graph and go through the whole steps?
Take the Google picture of the cabinet.
That's fine. I just thought up a problem I could do. It's good enough.
Okay, you can do it.
Okay, so let's just start from the graph. This is gonna look awful, but just bear with me. Okay, so we're gonna say that the resolution is what? How many bits you guys want? 8, 12, 3 bits?
8 bits.
Yeah.
Yeah, that's a lot of line to go through.
That's true. Just do 3. Okay, and then let's just say time goes to what? 8. And then like that, right? And then let's see, how many? That's 2 to the n, so that's going to be 8 words. So it's just 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's not even at all, but the process is still there. 1, 2, 3, 4, 5, 6, 7, 8. Okay, okay. This does not have to be perfect. I promise you guys. Let's do the first one. Let's sample it. How do we sample it?
You just, I just think take the one.
Yeah, we take the x values, right? So we're gonna find where we want our x values to be. So right here, and this is supposed to be a circle. Right here. Right, nope, I did that wrong. Oops. Okay. Here, right here, right here, right here. Yada yada yada. Y'all get the idea. Okay. So then how would we, so assume there's values here on this side, there's values here somewhere. How would we go about quantizing it?
You start with like wherever every tick mark is.
Yeah.
It starts at level 0 and then you just go up to like wherever
Yeah.
that range is.
So we just want to find the middle range here. So we draw little ticks right here, and then we just see if they're close enough. Y'all get it. Okay. So then let's move on to the more fun stuff. What would we say the step size is? So we have the equation, right? What's the step size equation? Y max minus Y min divided by our number of words, right? Or, steps, whatever she calls them. So what would the step size be then? What is n? What is n? Do you guys remember? It is in the slide right above this, I think. It's 2 to the power of n. So what would that be? 8, right? 2 to the power 3 is 8. Okay, so then that means our delta is going to be what? 3 minus 0 over 8. And I think that's like I can't do that in my head. Okay. Yeah, 0.375. Okay, that's a good deal. So then what would our quantization error be? Right? So that'd be 3 minus 0 over, 8 times 2. That is supposed to be across. Right? 8 times 2. Okay. Seems good enough to y'all? Okay, and then what if we want to find the SQ and R of this? Yeah, we use the equation, right? So what would our B be? So our B value, what would that be? 3, right? Because 3 is the number of bits, not the number of words. So what's our equation? Do you guys remember? I think it's like 1.76 plus 6.02 times B, right? Sorry for the bad handwriting. I'm leaning over the computer. So that means our value would be 1.76 plus 6.02 times 3. And I don't Calculator. Can somebody calculate that for me? Okay, 19.82. Does everybody online agree with that? I'm not an expert either. You can tell me. Well, Sebastian is an expert, so.
I would say that was correct.
Okay. All right, Sebastian says it's good. Moving on. Do we have any questions, by the way? You're welcome to ask questions. Just you're gonna have to sit on the mic. Okay.
So for the step size, when like finding the Y max and the Y min, that's
Sure.
just like from the graph.
Yeah.
Right? Okay.
It's real simple. They'll give you the graph on the exam. I think we had a homework problem over it, right?
I think so. Yeah.
Okay, so this is also very important. Somebody who took it last semester told me that they will ask about the ranges of these, so keep a lookout for those. I did put them on this slide after she told me that. So, or not this slide. It's the next one. Okay, yeah. Oh, RF transmission. I know this can kind of be a slog, but try to keep these separated in your mind. That's the best way to do this, in my opinion, is you want to read these in chunks because the way she does it in class, I love Diana Kogan very much, but sometimes it becomes a slog, right? So read through this in sections and try to categorize it in your mind. So maybe write out RF transmission and then write down each of these. And then when we move on to classification, there's also RF and light wave transmission. Don't get confused. So there's radio astronomy, and frequencies above 30 megahertz will propagate through the ionosphere. I don't know what that means. Lower frequencies will not. And then there's RF waves, and the speed of propagation of waves in the air will vary with altitude in the troposphere. And they'll bend back towards Earth. I'm sure that's a keyword she wants you all to know. Sky waves are going to be less than 30 megahertz. They will reflect off the ionosphere, and it's used for short wave radio. Just try to keep those keywords in mind because they will probably pop back up. These are the classifications of communication systems that we need to know. Analog and digital, which we're going to go over a little bit later. We did an ADC converter, but that's different from analog and digital communication, just to clarify. RF and light wave transmission. So light wave transmission is going to be, so we just went over RF, by the way, radio frequencies. Light wave transmission is a type of electromagnetic radiation and has a higher frequency than radio waves, and it must be enclosed in a guide, so optical fibers for long distances. An example for you would be in the Open Near lab that Fumagalli is doing. He has 150 kilometers of optical wire. I don't know exactly what he wants to do with it, but it's a lot of optical wire, and that's because they use actual, literal light to send communication messages. I think it's awesome. And then carrier or direct baseband. So it's based on whether the signal modulates at a carrier frequency or is directly transmitted. So I think we're going to go over that now. Okay, in a minute. Communication channels. So some communication systems are hardwired, so just cables, right? I think the example she put in the slides was a telegraph. I think another example you could think of, I can't think one off the top of my head. We live wireless. And then most communications are broadcast over the air from one antenna to another. That's important to remember. These things are being sent over antennas through the air. And optical cables are being sent through cables using light. Okay, let's see this. This seemed important. Humans can hear frequencies between 20 hertz and 20 kilohertz. Yeah, she talked about this in class, I believe. And humans can hear frequencies between 1 kilohertz and 5 kilohertz best. Funnily enough, that's where I think AM transmission runs through. There's many advantages to using a broad spectrum of carrier frequencies, one of which being that many simultaneous users can broadcast information. That's why when you turn the radio, you get to different channels. That's all just different frequencies, right? And different carrier frequencies are suited for different types of communication. So the carrier frequency that you use for your phone is not going to necessarily be the same as, let's say, a Bluetooth connection, right? They're not the same thing. Well, they're very different, but you know what I mean. Okay, steps for a communication system. I know this is awful. She does have a visualization on her slides. I believe it's the blocky ones, the big blocks, which each one of these. Highly recommend memorizing this. I think it was even on a homework, which means there's a high likelihood it's going to be on the exam. So very much try to memorize it. I know this isn't the best, but I'm still going to read it out for y'all. So we got the input message into our input transducer, right? the message carrier and signal, message signal and carrier, and the block is going to go up like this together. It will go into the transmitter, and then the transmitted signal will go to the channel from the transmitter, and then the received signal will go to the receiver, which will go to the output signal, and then the output will go to the output transducer, and then we'll finally do the output message. Again, there's only so much I can do to help you all with this. Really, just look at that visualization you put on the slides. It's going to be those blocks that, like, I'll even draw it out for you all because you can't really see what I'm doing. Stuff like this, right? You just did this, and a block, and this, and then a block, and this, and a block, and this, and then a block. In fact, do you want to run through exactly what these are really quick?
Input message is the first arrow, and
Yep.
then input transducer, and then message signal and carrier is the arrow that is pointing upward.
Yep. So this is going to be message signal, right?
Oh, yeah.
This is going to be the carrier. This is going to be because the carrier frequency is just a modulator, right?
Okay, yeah.
And this is a transmitter right here. Okay, transmitted signal goes out here to the channel, which goes to the received signal, which goes to the receiver. I forgot to write a block. And oh, I forgot to write another one. Okay. Output signal. That's another block down here. To the output transducer and the output message. So lots of words, right? How could you possibly remember this? So at the end of the day, all of these communication systems, you can even think of it like a bell curve almost. They all have a pattern, and halfway they will repeat, right? So you're going to get an input message, right, and an output message. These are the same, essentially, okay? You have an input transducer and an output transducer, right? The only difference is when you get to message signal and carrier. The carrier is just going to modulate that frequency, and then we're going to move on into terms that I don't know, so I'm not going to say very much after that. But once you get past this, you get to the transmitter, transmitted signal, the channel, received signal, and receiver. This can seem confusing when it comes to transmitter and receiver, but at the end of the day, if you can think of it like a bell curve where part of this, except for maybe this guy, is the same, everything down here will also be equal. So if you get really lost, you can't possibly get input wrong because, you know, the little blocks, the arrows going in will be the input message. And then transmitter and transmitted signal. I guess one way you can think about it is there's no way a transmitted signal can automatically go into an output transducer. Is there one way you can think about it? But just try to find ways to do it yourself because I can only do so much, right? I'm just repeating what's on the slides to the best of my ability. Okay. But yeah, try to think about it in a way that can make it look like a bell curve or a wave. Okay. Communication components. We just talked about these, but now we're going to go in a little more detail. So the input transducer will convert a message into a message signal, and it's transmitted over a channel, right? And the channel is, it could be air, fiber, wire, anything. I've heard some communication systems wanted to try to use water. That never went through for whatever reason, probably because it's very dense. The transmitter encodes the message with an encoder, funnily enough, and attaches a message to the carrier if it's wireless. If it's not wireless, I guess it doesn't attach it to a carrier because there's no frequency to modulate. The receiver, it converts the signal into an output signal, right? Into electrical impulses, I think. And if it's wireless, it captures the carrier with a bandpass filter, and it strips the message from the carrier, which means it takes only the information it needs from the carrier frequency. Then on the output transducer, it converts the receiver signal into an output message. Simple stuff. Spectral analysis. I believe there's a lot of infographics for this one, so you can go back and look through those. I will say my highest recommendation for studying for this exam will be going through those slides. There's a lot of stuff, lots of keywords, and if you can remember those, you'll be A-okay. So yeah, they can be represented in time domain and frequency domain. It's phasors. Right. The transmitter can combine message signals with carrier signals. We just went over that. The receiver uses band. Yeah, okay, I just talked about this. So one thing you guys might have gotten wrong in your quizzes. What filters do we use? Right? I know. Are we all thinking about the same question? It's the filter used to grab that carrier signal and then filter it out, right? I believe it's a band pass and a low pass filter. So just try to remember that. It's both. Okay. AM. I don't know about y'all. This was confusing to me too. You just got to stick through it, I guess. So it's got a variable amplitude and a constant frequency. So yeah, that's all I can really say about that. And we are using the A cosine omega t plus phi equation for anybody who's wondering. So it only carries frequencies less than 5 kilohertz, which is also what humans can hear best, right? It's going to be broadcast between 540 kilohertz and 1600 kilohertz. What does this mean? I don't know, but you should definitely memorize this. This is very important. They're going to ask you for the numbers. It's got a bandwidth of 10 kilohertz, and AM broadcast will carry farther than FM broadcasts do. And then there's frequency modulation, right? So one thing you can think of is you may not be looking at the names, and you may be looking at just the terms. There are lots of terms, lots of numbers. Think of amplitude modulation. It's got a variable amplitude, right? So if it's amplitude modulation, what's being modulated? What does modulation even mean? It's just changing. So the amplitude is going to change with amplitude modulation, and the frequency is going to change with frequency modulation. Is this news, or just kind of you guys already know this? It's capable of transmitting high quality sounds. It's broadcast between 88 megahertz and 108 megahertz. It's got a bandwidth of 200 kilohertz, a lot larger than frequency modulation. So FM broadcasts do have a higher sound quality than AM. Okay. It's the range of frequencies a signal can output. And then the half power is just 3 decibels, half power bandwidth. So it's going to pass between points where the signal level is 3 decibels and below its max passband values. This stuff you got to memorize. Okay, so do we have any questions about our previous stuff? Because now we're going to move on into analog and digital communication systems. For clarification, we just went over, I believe, yeah. So we went over, I think, carrier and direct baseband. Yes, we just went over carrier and direct baseband. And now we're going to go over analog and digital. So if we don't have any more questions, I'm going to move on. All right, sweet. So analog, you already know it. It's a continuous signal, like sound, light. It's infinitely variable, which means there's no like one set value you can just say it will be, and it's hard to isolate noise. Digital is a discrete signal. It's based on ones and zeros, and it's a lot easier to filter noise because you know what it's going to be. It's either going to be a 1 or a 0, right? So the differences. In analog technology, a wave is recorded or used in its original form. I believe she used the analogy of what is those? The vinyls, right? In digital technology, the analog wave is sampled at some interval, and then it's turned into numbers that are stored in the digital device. We did that for ADC conversion. Easy stuff. Okay. Digital signals can carry more information per second than analog signals can, because with the analog, you have to take every single bit. You can't just, if you cut out even a millisecond, there'll be a slight pause, right? But digital, it's being compressed into ones and zeros, and then we're going to go over how those can be transmitted efficiently. Digital communication systems have more immunity to noise and external interference, and they have a lot better error detection and correction mechanisms. And digital signals maintain their quality over long distances better than analog signals. So we got transmitter system components. So this is a transmitter from over here, right? Right here, this guy. That's correct, thanks. Transmitting, where is I? Right here. Okay, so we have an information source, the input transducer, and it may supply information in analog or digital form. It depends on what the input is, right? The ADC, we just went over how to do that. If the input signal is analog, it's going to be used to convert the information into a digital format. The source encoder, it removes any unnecessary redundancy and reduces the information signal to its most basic form. an encoder, as you know from digital systems, I hope, and if you guys aren't in digital systems, it's fine. But an encoder basically takes, I believe it takes a large amount of data and it simplifies it into a smaller address. Okay, so we get a channel encoder, so it reintroduces a small amount of redundancy that is carefully designed to protect the information from noise. And if you're wondering what redundancy is, we will go over that in a second. A baseband modulator, so it converts the digital information into an analog waveform that is shifted up to the desired carrier frequency. I know, lots of words. And the channel is just the medium over which the message is sent. We've gone over that like a billion times. Okay, so we got a demodulator now. All right, separates information that was modulated on the carrier. All right, the channel decoder and the source decoder. What does this mean? We encode the data, right? So we turn it into, smaller address. We send it over through the channel, right? So actually, I'll do this. We got the channel, so we encode it, right? We modulate it, so that way it's into a waveform that's shifted up. It goes through the channel, then to the baseband demodulator. And what that does is it takes our small amount, it takes our addresses, and then it's going to separate it, and it's going to blow it up back into our original signal, or as close as it can be to, and the decoder will reconstruct it. And it can detect and correct errors in noisy channels. And then the source decoder will decode the sequence back into a replica of the input signal. So if that makes sense to y'all, we got any questions? It's a lot. Huh? Okay. We got the receiver system components. We got the ADC. We've done this a million times. The output transducer, and it just takes that electrical signal, puts it back into a physical quantity. The source encoder, it removes redundancy. Source encoding is just the process of removing redundancy from a signal and keeping the most basic information that is needed to communicate the message. What is redundancy? I've said it like 3 trillion times. So it's any message content carried by a signal beyond the fundamental information being carried. I think one example the professor used was in a flash drive. When you have like 32 gigs, maybe 4 or 5 of them are redundant information, right? Redundant files. And redundancy will decrease efficiency. Therefore, source coding from the encoder that we just talked about is needed for designing an efficient low-power system. Because if we just take our signal and just send it through without encoding decoding, we're going to end up with a jarbled mess. Okay, the channel encoder, it's for error checking and correcting. It's going to set a transmission and storage rate at which one can accomplish an effectively error-free transmission of data over a noisy channel. And transmission and storage rate is going to be called the channel capacity. Keyword, channel capacity. Baseband modulation, transmitter. And because the physical communication channels can transmit only analog signals, digital baseband modulation will map the binary signal bits to analog carrier waveforms. And I know this is a little hard to visualize. She did put an infographic on the slide, also from McGraw-Hill. Mapping is accomplished by multiplying the analog carrier signal by the digital signal. So I believe I actually do remember what she did for this one. So it will be, you have your analog carrier signal. Sorry, no, you have the digital signal, right? And you're going to multiply it by our carrier signal. It's more like a wave, but that's beside the point. And then it's going to output what we want, right? That's how I want to think about it. The carrier signal, okay, it's been separated from our digital signal. We send the digital signal, and then we multiply it back into our original digital signal, is the way I understand it. Okay. And then it's the mapping, yeah. And then if you have more questions about how to visualize it, it is on the slides that Kogan posted. Okay. There are types of digital baseband modulation. Again, there is a big fancy infographic with lots of waveform analysis stuff, if you're interested in that. So we got the output at the channel coder. It's just the baseband digital message signal. The analog sinusoidal carrier signal, so that's just going to be the carrier signal. We have the ASK, amplitude shift keying. It's going to be the message signal that changes the carrier's amplitude. The FSK, the frequency shift keying. Message signal that changes the carrier's frequency, right? And then phase shift keying, PSK, message signal changes the carrier's phase. What is this mean? What is any of this for? I know you just heard the words I was saying and maybe not quite understood it. To be honest, this is a little confusing to me too. What we're thinking is number 1 and 2 are going to be the different kind of, so okay, the output of the channel encoder, that's just the output, right? The analog carrier signal is just going to be our carrier signal that we multiply into our digital signal, right? Is that something we can all agree on? These are the different kind of shift keying. How are we going to shift these, into what we want? So ask is just going to shift it to the carriers. It's going to shift the amplitude. So it's going to shift the A right here. I'm going to actually draw this out. So ask is going to shift A, right? FSK, whatever, is going to shift this guy. And PSK is going to shift this guy. Makes sense? It's a lot. It's a jumbled mess. Okay. So transmission modes of the digital communication. So we got serial and parallel communication. I think this was actually literally last week. So the process is sending data 1 bit at a time, sequentially over a communication channel or computer bus. Very simple. And it's way better for long distance communication because it's 1 little bit at a time. Parallel communication is a method of conveying multiple binary bits simultaneously, and it's faster for short data transmission, right? I believe one visualization she did. Oh, lovely, we're almost done. One thing she did was, I think, like this. This is a serial, and then the way she did this one was the parallel, like that. Okay, that was awful drawing, but it's more bits at a time. So this is 1, 1, 1. This is more like 3, right? But the downside of that is you can't make this go as long as this guy, right? Okay. So, what do I need to study? That's what you're asking. I mean, you're here, so you just went through way too much vocab and a lot of memorization. I know it's a lot. I will say when it comes to homeworks, I think even Nicola wrote a breakdown there on the board of what problems may be on it. Nothing is 100% confirmed, but when it comes to homeworks, I would recommend doing op-amp problems, a couple, just go over anything you're not particularly strong with, especially that the current analysis one for op-amps. I know I got my negatives wrong. There's going to be the Baud plots. If you're not familiar with those, it's on the exam, so I hope you are, but go over those. Maybe a couple KVL, KCL problems, just frequency, filter problems. Just go through those over the homeworks. The quizzes, I will recommend if you want to just double check to see if you remember your vocab. And then the slides. Go over her slides. I think it's only 2 weeks worth, but it is a lot of information. It took me, I read off of a lot of her slides for this, but it still took me a few hours to type it all up myself. I did not copy paste any of this, I promise. So it is a lot of information. It's a lot of information to dissect. I recommend sitting down, maybe categorizing it, especially when it comes to those frequencies. Not frequencies, sorry. The types of communication, right? We went over RF, light, analog, digital, I think one other. And sometimes in these slides, it can get very easy to jumble it up and get messed up, right? Okay. So these are my references. All the information in the slides that I used today can be found in Professor Kogan's modules. If you need anything else, I will be here. If you have any questions, I will be here, but we've reached the end of our 53 slide presentation. You go first.
So about the homework assignments.
Yeah.
So for test 3, the best homework assignments to go over would be like the last few that we've done so far.
I wouldn't say exactly that because a lot of them are filler problems, but if there are questions there that you struggled with, definitely do them again.